Have you ever really thought about how paint just sticks? Or how some foods seem to stay fresh forever? Well, there's this invisible science running the show, a force that is literally holding our world together. It's called surface chemistry. And believe me, it's not just about paint and food. It's the absolute key to some of the most important industrial processes on the entire planet. So, let's dive in.
Let's start with something you've probably seen 100 times. You've got a water pitcher, you pop in one of those simple charcoal filters, pour in some tap water, and somehow cleaner, better-tasting water comes out the other side. How does that even work? There are no moving parts, no electricity. It almost feels like magic, but it's not. It's actually a perfect, everyday example of surface chemistry in action.
The secret is a process called adsorption. Now, pay close attention to that letter. It's a D, not a B. We're not talking about absorption, like a sponge soaking up water. This is all about what happens on the surface. You can imagine the filter material is covered in these tiny invisible hands, which scientists call residual forces. And these hands are just sitting there, waiting to grab onto any molecules that happen to drift by.
So in this process, we've got two main players. The material that's actually doing all the sticking, in our example, the charcoal, that's called the adsorbent. And the stuff that gets stuck, the impurities floating around in the water, that's the adsorbate. The adsorbent grabs the adsorbate, and just like that, you get clean water. Pretty simple, right? Well, it turns out not all sticking is created equal.
Yeah, exactly. Think about pulling your laundry out of the dryer. You always find a sock clinging to your shirt, right? It's stuck, for sure, but it's not permanent. You can just peel it right off, no problem. This is actually a fantastic way to picture our first type of adsorption.
We call this Physisorption. It's a physical attraction, not a chemical one. The forces holding things together are called van der Waals forces, which is just a fancy way of saying it's basically molecular static cling. And because this attraction is pretty weak, the surface isn't all that picky about what it grabs onto. And just like that sock, the bond is totally reversible. The particles can come unstuck just as easily as they stuck on.
Okay, now let's flip to the other extreme. This is not some temporary cling. Oh no, this is a powerful, business kind of bond. You are not just pulling this apart. This is our analogy for the second, much stronger type of adsorption.
This one is called Chemisorption, and the name pretty much gives it away. Here we are talking about actual chemical bonds forming between the surface and the particle. This is no weak, temporary force. It's a genuine chemical change. And because you're forming very specific bonds, this whole process is highly selective. A surface is only going to bond with very particular molecules that fit just right.
All right, so let's put these two side by side. Physisorption, our static cling, is weak. Chemisorption, our superglue, is strong. Physisorption isn't picky. Chemisorption is super specific. But check this out. This difference in layering is really interesting. With the weak static cling, you can get multiple layers of molecules just piling on top of each other. But with the superglue of chemosorption, molecules form a direct bond right with the surface, so you only get one single perfect layer, what's known as a monolayer.
And you can really see the difference in power when you look at the energy that's released when these bonds form. Physisorption gives off a little bit of heat, maybe around 40 kilojoules per mole. But look at chemosorption, it can be as high as 400. That is a 10 times increase in energy. It just goes to show you how much stronger that chemical bond really is compared to a simple physical cling.
Okay, so we've got static cling and superglue happening on a molecular level. That's cool and all, but so what? Why does any of this really matter? Well, it turns out this simple act of sticking to a surface is the key to one of the most powerful and important processes in all of chemistry.
You see, when molecules get held on a surface, especially through chemisorption, they're held in just the right position. Their internal bonds get stretched and weakened just enough to make them way more likely to react with other molecules. The surface stops being just a passive parking lot and becomes an active stage, kind of like a chemical matchmaker. And this whole process has a name, catalysis. So a catalyst is basically a substance that dramatically speeds up a chemical reaction without getting used up itself. Think of it like a shortcut for a hike. A reaction might have this huge, steep energy hill it has to climb before it can happen. What a catalyst does is it provides a brand new path, a tunnel through the mountain with a much smaller hill, allowing that reaction to happen way faster and with a lot less effort.
So how does this whole thing work? It's like a beautiful three-step dance. First up, adsorption. The reactant molecules come in and stick to the catalyst surface. Step 2, reaction. While they're held there on the surface, their bonds break and rearrange to form a totally new product. And finally, step 3, desorption.
The brand new product unsticks and floats away, leaving the surface totally clean and ready for the next round.
Now, this process generally comes in two main flavors. When the catalyst and the reactants are all mixed together in the same phase, like everything's a liquid, we call that homogeneous catalysis. But what we've been talking about, where you have a solid surface acting on passing gases or liquids, that's called heterogeneous catalysis. And it's this different phase version that really powers so much of our modern industrial world.
And when I say it builds our world, I'm not exaggerating. The Haber's process uses an iron catalyst to create ammonia for the fertilizers that feed billions of people. Seriously, without it, the global food supply would completely collapse. The contact process gives us sulfuric acid, a chemical so essential it's used to make everything from car batteries to laundry detergent. And hydrogenation uses a nickel catalyst to turn liquid oils into solid fats for things like margarine. These aren't just small processes. These are trillion-dollar industries built on the simple science of sticking.
And hey, don't just take my word for how important this is. The huge significance of this field has been recognized for a long time. All the way back in 1932, the chemist Irving Langmuir won the Nobel Prize for his groundbreaking work in this exact area. He helped build the very foundation for our understanding of how these surfaces work, creating a legacy that continues to shape our world today.
So from that simple water filter in your kitchen, all the way to the processes that feed the entire planet, the science of sticking is absolutely everywhere. It's an incredible reminder that the surfaces we might see as passive and boring are actually dynamic, active stages where our world is constantly being built and rebuilt. It really makes you wonder, doesn't it? What other invisible forces are out there, hiding in plain sight, just waiting for us to understand them?